Hello guys, welcome to Exam List, and in this lecture series we'll talk about normalization of wave function. So in our previous lectures we saw that psi of x and t. Okay, so I'm talking about only one dimension to make things simpler, uh, but the reality is actually the reality happens in 3 dimension. So this is the amplitude. Okay, and we also talked about the square of the wave function gives you what? It will give you the probability. The probability has two things. One, if we are dealing with stationary states, then the probability will be independent of time. It will be only a function of position. And if we are dealing with states which are not stationary or where the energy is not definite, then the probability can be a function of both space and time. Now, having learned this, so what is psi of x? So psi of x is the amplitude at a particular x and a particular time t. Okay, so this is a function that has a distribution in space. For example, so consider this is the 1D x, then any psi of x is nothing but a distribution. So what kind of distribution? Maybe some distribution like this. Okay, so what kind of distribution is this? This distribution suggests that the maximum probability of finding the particle is here and the least probability of finding the particle is somewhere around here. So this is what it means. So psi of x and t is nothing but a distribution function. Now if I ask you what is the probability of finding a particle between x and x plus dx, so if you are asked to find the probability in a particular region, so what is this region? This particular region is dx, and that dx is from x to x plus dx. Then the probability is actually written as psi of x t. Okay, so what is the question? The question is the probability of finding the particle in a particular region. Then the probability is square of this into dx. So this is the probability of finding the particle. So what is this? This is the probability of finding the particle in a particular region, and that region is from x to x plus dx. Now we can write a very important result about probability. You know that the probability for the entire region must be 1. So the probability, if it goes from say 0 to x dash, then the probability of finding the particle from 0 to x dash is 1. Now why? Because the particle has to be somewhere between 0 to x dash. So what should be the condition now? The condition says that the probability of finding the particle, so that is psi of x comma t, okay, and its square, the mod square of it into dx. So this is the probability of finding the particle in region dx. Now what is the total region? The total region goes from 0 to x dash. Then what is the probability of finding the particle from 0 to x dash? Of course it is 1, because the particle has to be there somewhere between 0 to x dash. Or I can write more generally, if the region of space is not confined, and if the region of space extends from minus infinity to plus infinity, then the condition is that the total probability, I mean in the entire space, the particle has to be somewhere. So the total probability of finding the particle in the entire space is actually 1. So this is just a logical thing to say, because the probability has to be, the total probability is always 1, you know that. Okay, this is a logical thing to be said. So having said a logical things, now we go backward. So what is the backward thing? The backward thing says that if you are given a Schrodinger equation, remember Schrodinger equation? So it was I h cross del psi by del t. Okay, so if the state is a definite state, I mean a stationary state, then in place of I h cross d by dt, you will write just E psi. There will be just E psi. And if the probability is a function of time, then you use this kind of I h cross del psi by del d. So what is left in the right hand side? H cross square by 2m into d square psi by dx square. So this is the Schrodinger equation. Agreed. If there is a potential, then you need to add V into psi. This is the general Schrodinger equation at any potential. The reverse direction says any solution of Schrodinger equation, let any solution of Schrodinger equation be psi. Okay. So any solution of Schrodinger equation must satisfy this condition. It's quite logical because the total probability should be 1. So if you look at logic, then this equation is straightforward. This equation just says the total probability 1. If you go backward, then what happens is the backward idea says that any solution of Schrodinger equation must satisfy this equation 1. So backward idea says any solution of Schrodinger equation must satisfy equation number 1. This is called as the normalization condition. The condition, this particular equation number 1, is the condition imposed on the solution of Schrodinger equation, because only when a particular wave function satisfies this, then you can say that okay, you are dealing with a real thing. Or else if it does not satisfy, then total probability has to be 1. So if it does not satisfy this equation, it means that you are not dealing with a real quantum system. So any real quantum system must satisfy equation 1, and this one is called as the normalization condition. Okay, so normalization condition. So I hope you understood what is so this is a mathematical statement. Agreed. So any solution of Schrodinger equation must satisfy the normalization condition. This is a mathematical statement. So I hope in the next lecture we'll discuss more on quantum mechanics and wave function.